All right, welcome. This talk is called Prepare for JDK-9. It's one of 4 sessions that we're doing at Devoxx this year. Prepare for JDK-9 is all about going through some of the big changes that are happening in JDK-9 and what the implications of those changes are. We have another talk in this room later on today on introducing the module system itself. And tomorrow we have an advanced talk and a under-the-hood talk. I'll plug those at the end and give you the rooms for those. So my name is Bateman. Mark Reinhold is here as well. He's going to sit this one out maybe and take the questions at the end. Before I start, in case anyone may have misread the abstract, this is not going through all the other features in JDK-9. This is really mostly about the implications of modules, strong encapsulation, what it means for existing code. So just to get that clear. Right. So before we begin, I just want to, I have a slide here, Who's Afraid of the Big Bad Wolf, which is mostly to get a feel for whether people are a little bit nervous about some of the changes in JDK-9. So JDK-9 is still a bit out, but I'd just like to get a feel for how close people are to JDK-9. So if I could poll the audience for a few minutes just to find out how many people are currently on JDK-8. This is good. I see most hands up. And JDK-7? Good few hands too. Should I go back any further? 6? Hey. Further again? Okay, I won't bother with it. So for those that are keeping up with the JDK releases, I'm curious to know whether folks have been tracking the features and the changes going into JDK-9. So a quick show of hands as to who has been downloading the weekly JDK-9 early access builds to try out the changes. Okay, small number of hands. Who has been braver again and has tried the Jigsaw early access builds, which are JDK-9 plus the module system? Has anyone tried them out? A really small number of hands. Okay. Actually, I'll ask one last question. Who, put up your hands if you're nervous about some of the changes that are coming in JDK-9 that it might potentially break some existing applications? All right, maybe 10% of the audience. Okay, this is really what this topic, Prepare for JDK-9, is about, and hopefully we'll be able to address some of those concerns. So just at a high level, some background about what's proposed for JDK-9, and particularly what's happening in Project Jigsaw and what its goals are. It's mostly about trying to make the Java SE platform and the JDK a lot more flexible and scalable. It's about being able to produce reliable, compact deployments that are suited to run on small devices or in the cloud. It's all about improving security. It's all about improving maintainability. It's all about encapsulating security-sensitive APIs. It's all about encapsulating internal APIs, which is immediately leads into reducing maintenance for the JDK and also reducing maintenance for those working on libraries. It's all about, as Mark talked earlier on in the keynote, about moving away from and addressing at least some of the problems related to jar hell and the class path. It's also about enabling a whole bunch of other potential optimizations in the platform in the future. So they're just high-level goals for both JDK-9 and what we're doing with modules. The modularity landscape, I just want to get that on the table first so that it's clear what's going on, because there's all these numbers, both JSR numbers in the JCP, and there's also all these Java Enhancement Process, or JEPs, that are going on in OpenJDK. So within the Java community process, there is JSR 376, which is the Java Platform Module System. That is the JSR that is going to define the module system for Java SE 9 and beyond. Mark is leading that JSR, which mostly got going earlier this year. There will be another JSR for Java SE 9 for the platform itself. That has not been submitted yet. It's typically submitted a little bit later in the release because it essentially becomes the umbrella JSR for the release. So there's no JCP number for that yet because it's not submitted. So JSRs, JCP, that's all the standard stuff. For implementation, we do all of our implementation in the JDK now in the open and in OpenJDK project. And we have a project within OpenJDK called Project Jigsaw, and that is where we're working on the implementation of the module system. That's where the reference implementation for JSR 376 will be defined. There's a whole bunch of these JEPs, these Java enhancement proposals, and I've listed all of the numbers for the JEPs that we have here. JEP 200 is the JEP that is about the JDK modularization. Mark has showed spaghetti diagrams this morning in the keynote. I'm sure folks have seen some of the spaghetti diagrams from other conferences and previous Devoxxes. So we've been working on for a long, long time in the background on the modularization of the JDK, and JEP 220 is where you get a lot more information about that. JEP 21 is about reorganizing the source code and the JDK build around modules. So we've got a module graph. Now we're able to translate that into a source code layout and also completely change the JDK build so that it builds everything as modules. So it's very much an inward-looking JEP and something that we got in over a year ago into the JDK9 builds. Everything is organized by modules, built by modules, and that's really, really good. JEP 220 is about the modular runtime image. I have a couple of slides later on this because it's somewhat of a disruptive change, which is about changing how the JRE and the JDK look, the layout of them, because modules completely blurs the historical distinction that we've had between a runtime and an SDK. So a few slides on that later on. JEP 260, I'll be talking about it in this deck here, is about encapsulating the non-critical internal APIs. And JEP 261 is the implementation of the module system. That supplements the work that's going on in the JSR with all the implementation JDK-specific things. So I will cover those last three, the JEP 220 and 260 further on in the deck. So just some high-level background on the categories of the APIs in the JDK. I've talked a bit about JSRs and standard APIs. These are the APIs that typically are in the Java or JavaX namespace. These are the standard APIs. These are the ones that typically will have some historical connection with the JCP. Maybe they've been subsumed over time, but they are standard APIs. All Java-C implementations will have those APIs. There's a bunch then of JDK-specific APIs. These are historically been in the ComSun namespace. Some of the newer JDK-specific APIs that have been defined in recent years have been in the JDK.star namespace. Now, when I say JDK-specific API, I'm talking about documented supported APIs, but they're only supported within something that's derived from the OpenJDK source base. They're not standard JCP APIs. The ComSun namespace has historically been this confusing bag of internal APIs, supported APIs, and it's been historically very confusing as to know what can I make use of? What do I know will it be removed in the next release? I have no idea. Now, we put in a tactical solution for this in JDK8 with an annotation so that it's clear which of these ComSun and JDK-specific APIs are exported and supported. But this will be superseded by the module system in 9, of course. There's then all the unsupported APIs. Some of those are in the ComSun namespace. You'll typically see something like ComSun, XML, internal, blah, blah, blah. If you see internal in the name, it's typically JDK-internal API. Then there's all the sun.star. And the sun.star has been historically very, very troublesome because people have been making use of those APIs. Those internal APIs change over time because they're never intended to be used. And that's something I want to talk about in this presentation. So we've dug out, actually Mark dug out this is a page from the documentation from we think JDK 1.0 1.1. It's dated at the bottom 1996. And I'm just going to read out what it says about sun.star APIs. The sun.star packages are not part of the supported public Java interface. A Java program that directly calls any APIs in sun.star is not guaranteed to work, blah, blah, blah. We all know this. One thing actually to say is that documentation is all good enough, but the compiler was changed in JDK 6 to at least emit warnings when you start making use of these sun APIs, sun.star APIs or other internal APIs. some folks may have seen those warnings. Some people may just ignore those warnings. I will not poll the audience as to who ignores compiler warnings. So just some high-level just compatibility policies, and this has always been the case in the JDK and Java SE, is if an application is only using supported APIs in release N, then it should work on N+1 without any changes. It should not be necessary to recompile it. I think for the most part, this has worked quite well. There's, of course, incompatible changes that creep in accidentally, but for the most part, this has worked quite well. It's always been possible to remove supported APIs. It's not something that happens very often, but it has always been possible. It's even been possible to remove major features. That was a policy that was established, I think, in the JSR for Java C6. So how do we deal with managing incompatibilities? So this is at a high level, what happens is it's all about judging risk and judging based on real data what the possible impact will be. One of the wonderful things about when the JDK moved to OpenJDK is there's a lot more eyes on the code. There's a lot more people able to spot things that maybe the original author of the code may not, or the proposing a patch may not actually have recognized. So this is actually really, really good. So many people actually looking at a change before it actually happens to understand what the impact is. And a lot of people are forced to go through a lot of work and collect a lot of data before pushing through a change, because there is the concern around compatibility impact. Typically, what we do, at least the engineers working in Oracle, is we'll often make use of big corpuses of code to be able to analyze what APIs are using and how they're using. So this is just one resource. We also, of course, look at a whole bunch of existing products and libraries to get a better feel for how things are used before making changes. Whenever there is incompatible changes, we do attempt to communicate them, and communicate them as early as possible. So if you go back through release notes and JCP submissions for all the releases, you will see that there is communication about possible removal of APIs in the future. We've not really removed APIs, but 8 is an example, and I'll get into this 8 is an example where we've communicated possible future removal, and I'll get into that later in here. One other thing is when we are refactoring or removing some unsupported APIs, there is always consideration given to what possibly might be using it, even if it is unsupported, and where possible, replacements are provided as well. And then, of course, there's workarounds. I don't know how many people ever look at the extensive release notes that actually go out with every single JDK release, but there's inevitably there is a list of workarounds for particular changes. So there may be some change. It's making the code or the release do the right thing, but there's a possibility that someone is depending on broken behavior, and this is the workaround possibly to restore that broken behavior. This happens on a regular basis, and if you ever study the release notes, and they can be quite detailed at times, then this is often there. Okay, now we get to what I want to talk about in this presentation. There's 6 items on this slide. I'm mostly talking about the first 4. The other 2 are just more FYI, and I'll cover them very briefly at the end. So I want to spend a bit of time talking about the encapsulation of internal APIs, what that means, what the workarounds are. We've had to, in our effort to modularize the platform, which has been a multi-year effort, there are a small number of things that have to be removed, features and methods. I want to talk briefly about those. I want to spend a little bit of time on the binary structure of the JDK and talk about some other things that are being removed before briefly just mentioning the version string change and the underscore. So I'll start by showing a graph of this is a graph of the usage of internal APIs. The x-axis is the number of usages of a particular internal class, and it's the data set used for this is is there's a bunch of Oracle products, and there is a whole bunch of open source projects that we downloaded and analyzed. So there's just over 100 libraries that are used on this specific data set. So what we see here is that there's 125 usages of some internal class. And I'm curious whether there's any guesses as to what that class might be. Some people are saying unsafe at the SunMISC unsafe, and that would be a really, really good guess. On this particular data set, that's actually not quite right. On this particular data set, it's actually SunMISC base64 encoder. Okay, we stacked the deck maybe here, but these are examples of what originally meant to be, what were JDK internal classes. And in this data set, SunMISC base64 happens to be the one that's used more than SunMISC unsafe. I know if I use a different data set, it probably this would get reversed. If anyone wants to guess what the number 3 will be, anyone want to guess what the third one would be? Don't hear any guesses. So, in this particular data set, the third one happens to be base64 decoder. Okay, what I want to get into here is there's a couple of things to say about this graph. Is that there's a small subset of the internal classes that are clearly used a lot, and there is a big long tail of internal APIs that are used by only a small number of libraries. Once I go right down to the end of the graph here, I'm seeing only 1 or 2 usages of specific internal APIs. Now, what has been proposed is to try to at least categorize the usages of these internal APIs. And there's essentially 2 buckets, the non-critical and the critical. The non-critical are the internal classes that did not appear on that last graph. There's little or no evidence to show that they're used outside of the JDK. Also in the non-critical bucket are classes that are clearly used for convenience. I would put SunMISC base64 encoder and decoder in there. So there is, at least since Java SE8, there is Java util base64, and there's an encoder and decoder. There is no reason for any code outside of the JDK to be using the SunMISC base64 encoder decoder classes. They were just being used for convenience. There's dozens of base64 encoder decoder classes out there. Just on that one, we should have put in a base64 API 10, 15 years ago, and it would have avoided the dependency on this. So that's the non-critical APIs. The critical APIs are things like SunMISC unsafe, which is functionality that is completely impossible, or at least really, really difficult to implement outside of the JDK. Something like large parts of SunMISC unsafe, they could not exist outside of the JDK because they're so tied to the VM. So this is the high-level split between what was being proposed as the non-critical and the critical. And the JEP 260 proposal is as summarized on this slide. It's encapsulating all the non-critical APIs. So the non-critical are no evidence of usage, or they're probably only used for convenience. Encapsulate any critical APIs for which there is already a replacement in 8. I see there's a carriage return has ended up in this slide here. Ignore that. So if there's already a replacement in 8, there is no need for that to be that can be encapsulated in 9. And the important thing, and this is really important for those that are dependent on the SunMISC and some other critical APIs, is that we're not proposing to encapsulate these internal APIs in 9. What we are talking about doing, or proposing to do, is deprecate them, and then have a plan to remove them in 10. In addition, for any of there will of course be some bit of a workaround, and I'll get to that in a couple of slides' time, to at least be able to get at these encapsulated APIs via some command line option. So that is what the high-level proposal in this in JEP 260 is about. current proposal lists the following classes as critical internal APIs. SunMISC unsafe is there, of course. There's the support for signals. That is something I think we can look to define a standard API for, but there is code that uses it. SunMISC Cleaner, there is code out there that makes use of that, particularly around trying to forcefully free buffers and unmapped mapped files. There's SunReflect Reflection Get Caller class. There is a stack walking API that is being proposed for 9, but there is a lot of code, logging libraries, for example, making use of Reflection Get Caller class. So that's proposed as a critical API. And then there's SunReflect Reflection Factory, which is something that particularly serialization or deserialization libraries are going to be making use of, because they're doing things like trying to allocate objects without running constructors and other things like that are just not possible in the Java language. So that's what the current proposal is in JEP 260. When this JEP was published, one of the things that was said is that if anyone wants to proposes additions to that list, then come forth, but bring data with you to be able to justify why it should be not encapsulated in JDK-9. So far there hasn't been too much feedback on this. I think people have been mostly pleased that at least SunMISC unsafe and SunReflect are not proposed to be encapsulated, and that covers very much some of the core and critical libraries that people depend on or transitively depend on. But if there's other things that should be added to this list, get the data, come to the Jigsaw dev list with that data to back up the proposal. Now I'm going to go back to the slide on the. I'm going to go back to the data that backs the internal API usage that we had a few minutes ago. Now, hopefully this isn't too small. This is from the data set that we used to create that graph. This is the APIs that are used. So we see the base64 and base64 encoder and SunMISC unsafe at the top, and then we see this long tail. These are all color-coded. My apologies for if the color is hard to read, but orange is the critical APIs. So there's a C against any of these internal classes that are critical. So the SunMISC unsafe, the SunReflect Reflection Factory, the APIs that are listed on the last slide appear in orange on this slide. The non-critical APIs are the ones that are in purple, and against them is a release number for which release there is an API available. So I mentioned about SunMISC base 65. I mentioned about Java Util base 64 being a new API in Java SE8. Then that is the reason why SunMISC base 64 encoder and decoder have R8 against them. There is a release 8 that has that supported API, so there's no reason for the SunMISC APIs to be encapsulated. There's a bunch of APIs that are listed down here that are non-critical. So the ones that are in red are the non-critical, where there's no replacement planned because they're probably just used for convenience. So there's a whole bunch of internal XML classes within the JAX-P repackaged implementation that are being used by some libraries. There's no plan to provide these, no plan to designate these as critical APIs. So that's just the classes for this 110 products that were actually, and libraries that were used for this analysis. Now I want to move on and just talk about how do you find the JDK internal usages. So we have a tool that does static analysis. The JDEPS tool, we're going to use that in a number of the presentations on modules tomorrow. And I'm curious whether people have used, are familiar, let me just quickly poll, are people aware of JDEPS? Okay, I see a small number of hands. Okay, JDEPS is a tool that does static analysis of jar files, is a simple way of putting it. The tool is there in JDK-8. We developed this as part of JEP 162 to provide a simple way that you can run this tool on essentially a class path of jar files and find out what APIs they're using. It can tell you what internal APIs are using. It can find out what the dependencies are between different jar files. There's a whole bunch of very useful options. So if you haven't tried out JDEPs and you have JDK9, at least try it out, or sorry, JDK8, then try it out because it's really, really useful. We've improved a lot JDEPs in JDK9, and we have improved it yet again in the Jigsaw builds, where we have a whole bunch of other options that will actually aid people creating modular declarations. So JDEPs is a command line tool. There's also the Maven folks have a JDEPs plugin that is useful if you're using Maven. So you can have it run in your build to look at your artifact to see does it have any dependencies on any internal APIs. You can also have it run on your transitive dependencies to find out whether there's any library that you're using that might have a dependency. So the option that I want to show on the next slide is the option JDK is called JDK internals. The example I'm going to run this on is I've just taken one of the jar files from the Glassfish 4.1 distribution, and the option I'm passing is JDEPs and then JDK internals, which is a special option to report JDK internal API usage, and then I'm just giving it the name of the jar file. There's a whole bunch of ways that you can actually run JDEPs. It's become a little bit of a Swiss Army knife of static analysis tools. I'm just picking one usage for this slide. Now we'll go and look at the output, and we're going to switch to a smaller font to be able to see the output of this jar file. So what we have is the output is showing me what the code in this jar file depends on. And it's listing me out that there's code in there depends on Java Base. Java Base is the core module of the system. It's where Java Lang object lives. We'll be getting into that in the other presentations today and tomorrow. And then it lists me a whole bunch of other classes in this jar file. They're all in the package ComSun Enterprise something, and they have dependencies on internal APIs. In this case, the code in here is clearly making use of a lot of Sun Security, X509 and Sun Security Util. So these classes are part of the internal security framework in the security libraries, part of the JDK, and they're being used by code in this jar file. You can see there over on the right where it's flagging them as JDK internal API and what module they're in. So there's a lot of code in here that's making use of internal APIs. One other thing that the tool does is it has a small little database that goes with it that gives a mapping to supported or newer APIs. In this case, someone that's using the X500 name type, which is in Sun Security X509, well, maybe that code should really be using, there's an X500 principle that has been in the platform since Java C 1.4. So it's providing a mapping there. When it recognizes that there's a possible standard or JDK-specific replacement for that, then it will actually print that out as well. So this is a useful tool to at least give hints. It may not be easy to refactor the code here to make use of X500 principle, but at least it's making folks aware of it. So that is a static analysis of one jar file to show, and with JDEPs to show how you can find out what internal APIs are being used. I want to actually show what happens at runtime if you start making use, if you're starting up Glassfish in this example, and it starts to run some of the code in this jar file, what will happen? So assuming we have not recompiled Glassfish for running with modules in JDK9. Suppose we've kept whatever it's compiled with 7 or 8, and we try to run it. What will actually happen? And this is what happens in this specific case. We get an illegal access error. It looks a little bit scary when you see it first, but an illegal access error it would be if you had. Typically, a legal access error means that you've got some kind of a mismatch between your compile time and your runtime. It may be that you actually have a reference to something that's private but was actually public when you compile it, for example. And modules has that effect. We'll be talking in the other presentations about what what it means to be public and whether a public type is accessible or not. But with encapsulation of internal APIs, you may have public types in these JDK internal packages that are public, but they're not accessible. So this code in this jar file is attempting to access, in this case, Sun Security Provider policy file, will actually get a legal access error when it attempts to access that type. There's other information in this exception to indicate what modules are involved. Ignore some of the details for this. We'll be going through in the other presentations on modules how to read these exceptions a bit better. So that's just one example from Glassfish to show what would happen if you ran this code with strong encapsulation. I'm going to pick a second example. I'm sticking with the G's. I'm going to just pick Gradie this time. And I've got a compile Java task that I'm going to run, and it actually fails when I try to run it with my jigsaw builds. Why is this? I've highlighted the error in red here. It says, could not create an instance of type ComSun tools JavaC API JavaC tool. When I look at this first, it looks to me like Gradie is unable to launch JavaC for some reason. What's going on here? But Gradie is useful in that you can get a lot more information by rerunning it with the -- stack trace option, and it should give me a lot more detail as to what exceptions are being thrown. So I'm going to rerun Gradie again, this time with the stack trace option to try to get some of the exception. I've removed most of the exception here, and I've gone straight down to the bottom of the stack trace, which is where I actually see the cause of the exception. In this case, it's an illegal access exception. The previous slide I had an illegal access error, which is I'm attempting to resolve a static reference to some type in an internal package. In this case, there's clearly some code in Gradie that is using co-reflection to get at some internal type. In this case, it's some internal type in JavaC, the Java compiler. So again, the exception is explaining what is going on here. It says this is an internal type in the JDK compiler module. Someone outside of that, in this case it's the unnamed module, is attempting to access that. We'll explain in the under the hood talk all about unnamed modules. So this may all look a little bit scary. This is the implications of strong encapsulation. It means existing code that is making use of internal APIs now suddenly stops working. But don't panic. I want to now talk about the command line option that to at least be able to get code that is existing code to work at least by just adding to the command line. So the option we have in our current jigsaw builds is called xAddExports. You essentially give it the list of these internal packages that you want to be exported to have some existing code continue to work. It might look a little bit, the option here might look a little bit verbose. What's going on here is there's the source module, the package, and who it's being exported to is all encoded in this command line option. In this case, in order to run Glassfish, and we can bring up Glassfish just fine with our jigsaw builds, but we have to give it the exports so that these internal security classes that Glassfish is using are exported, or at least in an exported package, so that Glassfish can continue to work exactly as it did previously. Now, the Glassfish folks are our friends, and I didn't want to pick on them for just this particular presentation. They have been testing for quite some time with the jigsaw builds, and they have an issue in their JRE that actually tracks addressing this issue. There's I think about 10 different issues that they have in their JRE. Some of them are easy to solve, some of them are not easy to solve. But the good thing is that by at least working with the early access builds, finding these issues, finding solutions to these, and particularly some of these old code, then it helps get them in a much better place so they can actually run on 9 when 9 eventually ships. So xAddExports is the option. Essentially what it does is breaks encapsulation. This is the syntax of it. Source module package equal to the target module. And you can list this many. The option can only be listed once, but the value can encode multiple source modules, packages, and targets. So that is what encapsulating most of the internal APIs means. It means that existing code that uses those internal APIs may not run, but there is at least a workaround to keep existing code going if necessary. So that's the biggest change that's happening, or the biggest thing that modules will mean for existing code that continues to run on the class path. So I want to move on now and just go through some of the other changes that are going on. So I'll talk about the removal of methods. So the JDK is absolutely huge. There are tens of thousands of methods. There's thousands and thousands of classes in the public API. As part of preparing the platform for modules, we recognized a long time ago that 6 methods have to go. And these are the 6 methods that we are proposing to remove in 9. They have been removed from JDK 9 since the first build. So right at the end of 2013, before even JDK 9 build 01 shipped, these methods were removed so that we would give a maximum time to anyone that might have a dependency on those methods to be able to make use of replacements. In the case of Java Util Logging Log Manager, there is new methods that replace those. In the case of the 4 methods in the Pack 200 packer and unpacker, we have not found any usage whatsoever of these outside of the JDK code base. So there's no replacement plan for those because we haven't seen any usage of them whatsoever. So these are the only 6 methods that we're planning to remove from the standard API, which I think is actually quite good given the size of the platform. In this particular case, as I said, we've known about these 6 for a long time. And it's been documented, they've been deprecated. When Java C8 which was submitted to the JCP, then these were actually flagged as being deprecated and to be removed in a possible future release. So they're the only 6. So I think that's actually not too bad. This other change, though, which is the changing the binary structure of the JRE and the JDK, is something that is a lot more disruptive. So there's a whole bunch of motivations for doing this, and some of this will be clear once I show the next number of slides. But a big part of it is moving to modules will completely blur the historical distinction that we have between the JRE and the JDK. In some of the other presentations on modules, you'll see that we're actually taking libraries, we're linking them with modules, and we're producing new runtime images. The structure that we have in the JDK and JRE don't lend themselves for that. Also, using jar files is a really inefficient and probably one of the worst ways that we can actually store classes and resources for the platform, particularly for startup and some of the optimizations that we want to do. So this changing the structure of the JRE is a disruptive change. It's something we wanted to get into JDK 9 really early, so it's in JDK 9 builds for about a year now, mostly to give time for the tools to catch up. Because if you're a compiler, you're an IDE, your tools that are making use of RT.jar and so on, you're depending on the structure of the JDK. So changing that structure has impact on the tools, and it's going to take a while for those tools to catch up. The good news is this is the first time that we will ever have a supported interface for accessing classes and resources in the JDK or the JRE. We've never had a supported way of doing this before, and now we do, and it allows tools running on 8 or 9 to be able to access a JDK 9 image, which is really nice. So just a quick summary on the layout of the legacy JDK image. I would hope anyone using the JDK will recognize this. There are two bin directories. There's a bin directory at the top level. There's a bin directory in the JRE directory. You will actually find the same tools, mostly in both directories. That's a little bit strange. It's a little bit of an accident that goes back to 1.2. There are 2 lib directories. The runtime classes are down in JRE lib. classes for tools, we're in tools.jar at the top level lib directory. There's also a bunch of other jar files in there that make up the rest of the mess of the runtime, and they all have their history and story associated with them as to how they ended up in separate jar files. The lib directory and other parts of the and other directories are a little bit of have historically been a little bit of a mix of files that are intended to be changed because they're configuration files, security policy files, and so on, and a whole bunch of other files that were never intended to change. You can edit some of the configuration files in the JDK and it won't start up. You can change it so that things actually break. Some of these files were just never intended to be documented, never intended to be edited. So we've used the opportunity with reorganizing the layout of the JDK to be able to address those kind of issues. And what we've moved to with JEP 220 is the new modular runtime image. And it's a very, very simple layout. There's a bin directory where you'll find all of the launchers, so that's where the Java launcher is, that's where you'll find Java C and so on. There's a conf directory, which is where any of the configuration files that are intended to be edited or to customize the JDK or the runtime, that's where those files are. All of the other files that really are not intended to be edited, they have been moved elsewhere. They're not in the conf directory. Only the files that are intended to be edited are in the conf directory. There's no JRE directory, there's no two bin directories, and most importantly is there are no jar files. There's no rt.jar, there's no tools.jar. The classes and resources that the JDK is using that are part of the runtime, part of the runtime image, they're now in this internal format. That will change over time. It's intended to be optimized very much for the JDK usage. It's intended to enable us to do a whole bunch of other optimizations over the next while. Mark mentioned about AOT and the linkage to that. We can optimize things for startup. We can do various compression. We can do a whole bunch of other sharing between classes and other things that you need in order to get the footprint down to run on embedded systems. So it opens up a whole new world to do these kind of optimizations over the coming years. So that is what the layout is. And as I said, this is in JDK 9 for over a year now. It's taking some of the tools caught up quickly. It's going to take time for many of the other tools to catch up on this. So this is a disruptive change, and I would hope by the time JDK 9 ships that almost all of the tools will be able to work cleanly with the new image layout. There are two features that have been removed. Or misfeatures is how some people have described them. The extension mechanism, which was a way to drop arbitrary libraries into the JDK or the JRE and have them their types be visible. Very problematic mechanism. That has been removed. That was also flagged in Java C8 for removal. The other thing that has been removed is the endorsed standards override mechanism. Most people probably have not heard of this mechanism. It's typically the way that app servers use to provide newer versions of standalone technologies and endorsed standards. Same mechanism for both. So historically, app servers would need to run with a newer version of JAX-B or JAX-WS or the common annotations or some other standalone technology. Or endorsed standards, maybe the W3C API or the Corb APIs. This was the mechanism for allow them to override what's in the JDK. Moving to modules opens up the possibility of doing this in a much cleaner way. And in our Jigsaw builds, we have an upgrade module mechanism which changes the unit of replacement to be module. So if an app server wants to run with the EE version of the common annotations, the JDK only has the subset of that, which is the SE version of the common annotations, then that can be packaged as a module, put on what we call the upgrade module path, and that will cleanly override and hide the module that the JDK ships with. So this is a lot better mechanism. So endorsed standards override mechanism goes away, and we have the new way to replace be able to upgrade modules with alternative versions. A couple of other little changes that are going on, and these all stem from changes to the implementation. So modules fundamentally changes a lot of things. Our class loaders are no longer, or at least our application and extension class loaders are no longer instances of JavaNet URL class loader. Any code that depended on that, and that's very much a highly implementation specific the assumption that there would be instances of this type, they would break. What we know as the boot class path is gone. Everything is modules now. So there is no way to replace or to use the prepend classes to put them on the boot class path. There's ways of patching modules that we can get into in questions on modules, but what we know as the boot class path has been changed very significantly. Associated properties with the boot class path are also they will also go away. They're not quite. It's not quite there with the Jigsaw builds where we're 95% there. JEP 261 has all the other possible implications. So we've put a lot of effort into attempting to identify all these other implementation-specific assumptions that code might make, and they're all documented in the final or the end section of JEP 261. If you want to Google for that, it's quite extensive. So just to give an example about for one of these, I'll go back to Gradle, and my apologies if there's anyone working Gradle here. I've just randomly picked this one because it just happens to be one that has an assumption in its code somewhere that the application class loader, or I think it actually assumes the system class loader is a URL class loader, which it isn't when you run with Jigsaw builds because the application class loader are completely different from what they were in previous releases. So there is code somewhere in Gradle that happens to get a reference to the system class loader and then blindly cast it to a JavaNet URL class loader, and it gets a class cast exception. Now, this, by the way, is one that apparently is straightforward to fix in Gradle. It's all about some hack that was put in a long time ago to work around command line lengths and limits on Windows. A lot better way to do that with JDK9 because there's arg file supports. You can, if you've got command lines with really large number of arguments and they won't fit on the command line, then at least you can put into a file and use the add arg file syntax. So this is just an example. This one is not really tied to modules. This is really just an implication of some implementation change. So every single JDK release, there'll always be some internal changes and some refactoring that'll go on. Something that makes a dependency on what an implementation type might be is always at risk of breaking. So that's just one example. So two final things that I want to cover. These are not core to Jigsaw. They're not core to modules. They're only things I just wanted to highlight so that folks are aware that moving to JDK9 means dealing with the version string change. So there's a JEP on this, JEP 223, that has a lot more details about this. So the versioning string format in the JDK has always been really confusing. I'm just going to read out a little section here from the JEP, which actually helps to explain some of the motivation for this. Which release contains all the most recent security fixes? Is it JDK7 update 55 or JDK7 update 60? It looks like JDK7 60 is 5 releases later than update 55. Therefore, it must include more security fixes. But that assumption is incorrect. These two releases contain exactly the same security fixes. So over time, the way the version string has worked and the JDK has got quite confusing. Security releases have been bumping by 5. Update releases by 20. How do you know which one is more secure? It's really confusing. So this issue is finally being looked at, and that's what this JEP is all about. The important change is that the leading one goes away. So this is a table. I've pasted this in from the JEP to show what the version, if we continued with the current scheme, would be versus what it will be when the version string scheme goes into JDK9. It's not in the JDK9 build. So if you try it out and you start looking at Java-version or the system properties, you're not going to see a change just yet. But I would hope that would get in soon. So the important thing is that the builds are being reported as version 9, not as 1.90. And you'll see as you work through the examples in the JEP how it's actually going to change. Where this may possibly be an impact for existing code is where there's a dependency on the value of these properties. There is code out there that parses the value of java.version. So today, if you take the JDK9 builds, java.version is going to be 1.9.0. When 9 ships, then we expect it will just have the value 9. So there may be some code out there that might get tripped up by this. It may assume that there's a leading 1 dot in the beginning of the string. So this is just something to make folks aware of. To my knowledge, from anything that's been tested so far, it's only been a small number of cases where code has been found to be really, really dependent on the version string. So, but it's just something to be aware of. If you have code and you maintain a library that maybe is doing some JDK version tricks to work around something or do something different on particular JDK versions, check it out just in case that it may be impacted by this. And the final thing I just wanted to point out in this presentation is the underscore. This is an odd one, because this is solely a source incompatibility. If there's code that's already compiled with some previous version that's using the underscore, it will continue to work. But code that's, if you attempt to recompile the code and it has an underscore as a single character identifier, it will no longer compile. So I just wanted to make people aware of this. This has nothing to do with modules. This has been flagged for quite some time. There was a JEP on this. I just wanted to point it out as something to think about in case you have code that might do this. The JEP to find out more about this is JEP 213, which is the milling project coin JEP, which has a couple of little updates to the language. By the way, if you have code that is using the underscore, you will be getting a warning in JDK8 already. So if you compile it with Java C, then you will be getting a warning already. So what can you do to prepare for JDK9? Well, the most important thing to come away with is the JDEPS tool. It's really, really useful. It's a Swiss Army knife of static analyzers. It's really, really useful to be able to look at your libraries or your own code, any libraries that you're actually making use of to see whether you have any internal API usage. I wanted to bring up about the version string and the underscore just to be able to make folks aware of that. And then for anyone that is working on tools and the changes to the runtime structure and everything related to JEP 220, removing rt.jar, removing tools.jar, that has a big impact on tools. So if you're maintaining any tools, then check that out. And finally, to say is that we have both JDK9 early access builds and we have Jigsaw early access builds available for anyone to try out. I know that sometimes people get confused between the two of those. The JDK9 early access builds go out like clockwork every week on the java.net download site. The Jigsaw builds go out on a slightly irregular basis. They are whatever version of whatever point of JDK9 that we're synced in Jigsaw at that particular point. They're that version of JDK9 plus the module system. So we've pushed out 3 or 4 of those now in the last two months for people to try out. And it's the Jigsaw builds is what has the strong encapsulation. That has the module system. If you try out the JDK9 builds, then you can continue to use a lot of the internal classes because there's no module system in 9 yet. And that's all I want to talk about today in this session. So we're doing the intro talk in this room later on today. That is very much a gentle start on modules. It's covering the basic concepts that you'll find in the State of the Module System document. Tomorrow then we have the advanced modular development, which deals with real-world cases and migration to modules. And then we have the really, really advanced under the hood talk tomorrow. in room 5. So that's the other talks that we have here. For more information, Project Jigsaw page on OpenJDK. Jigsaw Dev is the mailing list that we use. There's the links to the early access builds, both the JDK-9 and the Jigsaw builds. JDEP's tool is really useful. That also has links to the wiki page where there's more information about internal APIs, and I've also put a link there to the JEP 223. So I think we're done. If anyone has questions, then it would be great if you could find a microphone.
Or I'll bring you one.
Mark has a microphone.
Hello. I don't know, maybe I didn't get it, but what kind of identifier or keyword is underscore? What's it used for in JDK-9? The error said it was a keyword.
Do you want to talk, Mark, about how it might possibly be reused? Without mentioning Scala?
Mentioning what? The underscore in JDK-9 has no special meaning other than that it is no longer a legal identifier. Prior to JDK-9, you could use it as an identifier. There are a couple of libraries that have APIs that do use underscore alone as a single identifier. It's basically, underscore, you can think of it as a bet on the future. There are some ideas that we've thought about a bit, especially in exploring some of the work around Valhalla, if you're familiar with the value types for Java. And you know, there may be some point in the future where we want underscore to have a special meaning. Not necessarily the special meaning it has in Scala or other languages. We can't promise that we will want to do that, but if we're going to do that, then we should take action now to prevent underscore from being more widely used. And that's why we deprecated it in 8 to make it generate warnings, and we're taking it away in 9. We might lose this bet, and we will have wound up annoying people for no good reason, but sometimes predicting the future is hard. Another question?
Can we try the Jigsaw? Is there a build that we can use? We can show in a Java user group or something?
Yep. Download site there.
Okay.
So follow the resources. On the Jigsaw page, there's links to all the JEPs that I mentioned and a whole bunch of other material, and the binaries are available there as well to try it out. Mark is getting his exercise today.
Will there also be changes to the web starts class path?
Nope. No changes to web start are planned right now.
Yeah, question. I know EE and SE are two different worlds, but do you think in EE9 we will have a bit more modular app servers? Because you mentioned app servers and modules.
Yes.
Thanks.
No, definitely. I mean, that's all part of the, if there's a grand vision here, we hope that a future version of Java EE, perhaps numbered 9, will have modules incorporated so you can have a modular WAR file or whatever. And we've already spent lots of quality time with various EE spec leads to make sure we understand what they think they're going to need so that they can do what they need to do.
Is there any plan for async await, like in async await, like in C#? Asynchronous programming, async await.
No. Come to ask the architects, and we could riff on that.
What about the delivery time frame? You have still a plan?
I think you're asking about the JDK-9 schedule. Software schedules, they are what they are. You do your best. Sometimes you change the schedule. But the schedule is what it is for now.
Yeah.
Do we have any more time? Is the clock blinking red?
You got 1.5 minutes.
Okay.
You can get in another couple of 100 meters of running.
No. Kirk, you get too much airtime. I'm sorry.
So currently the Java compiler AST is probably not public API. Are there any plans to make it public API? The Java C.
So the example
AST.
okay, so the example I used there, I think, was mostly launching the compiler, which doesn't, I think, require access to the AST. I think in that particular case, it would be possible for that code to just use JavaX tool API to launch the compiler. But
Isn't there a view on the AST that is supported? I can never keep this straight in my head.
Yeah, I'm not sure which of the Java C
Yeah,
APIs.
the internal AST
yes.
certainly isn't, but there is a non-SE standard but supported AST that from the JDK perspective we support. You just might not find it everywhere. Kirk, you don't have much time.
IDE support.
Yep, IDE support is good.
Do we have it yet? Who's supporting it right now?
Who's supporting Jigsaw features in IDEs right now? Nobody. Nobody, but we actively talk to them.
Right.
Yep.
But just to say, is each of the IDEs have already put in work to support the changes that are in JEP 220. So they're working with the JDK9 builds, which is really good. But the module builds, Jigsaw builds, they're only just brand new. The IDEs, it's going to take some time for them to support modules.
All right, time's up. Thank you very much.